Hello, myself Saurabh Nashkor, Assistant Professor of Chemistry at Gargi Memorial Institute of Technology. In my previous lecture, I discussed about Gibbs free energy. Today I will discuss Ellingham diagram and Gibbs Helmholtz equation. First, I will discuss some features of Ellingham diagram. Graphical representation of standard Gibbs free energy change versus temperature plot in the formation of oxides of elements is known as Ellingham diagram. Del G naught versus temperature curve for metal to metal oxide shows positive slope because the del G decreases with temperature. Second point is curves in the Ellingham diagram shows straight line with positive slope unless there is a change in state. Third point is with increase in temperature a point is reached where the graph crosses the del G is equal to 0 line. Below this temperature the free energy of formation of the metal oxide is negative and the oxide is stable. Above this temperature, the free energy of formation of the metal oxide is positive and the oxide is unstable. Stability of metal oxide decreases with increase in temperature. And last one is it can be explained from Ellingham diagram that a metal will reduce the oxide of other metal which lies above it in diagram. Now we will learn what is chemical potential. The partial molar Gibbs free energy of a constituent in mixture at constant temperature, pressure and mole is given by chemical potential. So here constant will be temperature, pressure and mole number, and this is the partial molar Gibbs free energy with respect to number of moles. And this chemical potential is denoted by mu. Now this is most important, Gibbs Helmholtz equation. Equation for variation of free energy, that is G, with temperature and pressure, that is P and T, is given by dG is equal to VdP minus SdT. Now when pressure is constant, then dP will be 0, so this term will be vanish. So we can write dG is equal to minus of SdT. Now let us consider a change in which initial state is S1, G1 and T1 and the final state is S2, G2 and T2. Here S is entropy, G is Gibbs free energy and T is temperature. So we can write dG1 for initial state, we can write dG1 is equal to minus of S1 dt, and for final state we can write dG2 is equal to minus of S2 dt. Now by subtracting dG1 from dG2 we will find minus of S2 minus of S1 dt will be there. So and this is nothing but change in Gibbs free energy, because Gibbs free energy of final state minus Gibbs free energy of initial state is given by change in Gibbs free energy. So del G is equal to G2 minus G1, and this is change in entropy. Entropy in final state minus entropy in initial state. So in place of S2 minus S1 we can write del S. So when this del T will come in the below side, so we will write del of del G by del T at constant P will be minus of del S. Now we know from Gibbs free energy equation del G is equal to del H minus T del S. So del G is equal to del H minus temperature, and in place of del S we will put this one. So final equation will be del G is equal to del H plus T del of del G by del T at constant pressure. This is Gibbs Helmholtz equation, and this equation is applicable to all processes occurring at constant pressure. Now we will learn application of Gibbs Helmholtz equation. To predict spontaneity, when del G is less than 0, the process will be spontaneous, and when del G is greater than 0, process will be non-spontaneous, and when del G is equal to 0, process will be in equilibrium. Second, to find thermodynamic parameters during electrochemical cell operation. And last one is to find enthalpy change at constant pressure. These all are the application of Gibbs Helmholtz equation. Now we will learn Helmholtz function, which is denoted by A. This is the maximum amount of energy isothermally available to a system that can be converted into useful work is known as Helmholtz function. And the mathematical expression for Helmholtz function is A is equal to U minus Ts. Here A is Helmholtz function, U is internal energy, T is temperature, and S is entropy. Now, A is a state function and extensive property. And the minus of change in Helmholtz function is equal to W. W means work, and this is change in Helmholtz function. So from this equation we can say that decrease in Helmholtz function, minus of del A means decrease in Helmholtz function, is nothing but the maximum work that can be obtained from a system. This is the work, and this is when change in Helmholtz function is negative, then work will be maximum. Now we will see some short questions. When a process occurring from, or we can say conversion of carbon dioxide gases into dry ice. Here process is occurring from a gaseous state to a solid state. So here randomness will decrease. Gaseous states randomness will be higher, and in solid state randomness will be lower. So randomness decreases means entropy will be decreasing. So entropy decreases here. Inversion temperature of Joule-Thomson coefficient is 0. During mixing, their randomness will be increasing, so entropy will be increases. During isothermal mixing of ideal gas, entropy of the surrounding will decrease. Entropy of the universe is always increases, and condition for spontaneity is del H is less than 0 and del S is greater than 0. Free expansion of ideal gas, del T will be equal to 0 and del S will be greater than 0. In my next lecture, I will discuss Maxwell's relation and second law of thermodynamics. Thank you.